So what exactly is cloud destruction? Cloud destruction physics means that we're taking the massive calculations that are required for large-scale destruction physics, and we're going to process them on the cloud. And then we're going to communicate that back to the game server that the clients are connected to. The client can then process the visual and audio elements using these calculations and also some client-side prediction. OK, so by default, the server communicates the position and orientation of the objects, but we're going to need a little bit more information than that for our audio systems to work. If we take all of the data that's provided to us and we try to send it to the client, it is going to just tank performance immediately. Right? So we have to figure out how do we get the most relevant data that we can reasonably fit through that server-client bottleneck. Before we get too deep into that, I want to throw out a few key terms to give you a broad overview of our systems. So our larger term destruction objects is going to break down into two categories, the Havoc bodies and GPU objects. Havoc bodies are going to be processed by the server, and they're going to have a full range of physics behaviors. We'll show you a little bit more about that soon. GPU objects are sometimes known as GPU chunks, and they only exist on the client. Okay? These are created and controlled by the graphics shader, so they only really exist while they're on your screen. They consist of only a few materials and exhibit a limited number of behaviors. Static geometry is a collidable but non-damageable surface. It's basically the floor. Impacts occur when destruction objects intersect with other destruction objects or static geometry. And destroys are when Havoc body splits into children. So this is different than how we do it in campaign. In campaign, we swap it out for a damaged prop, or we just get rid of it completely. Here, what we're going to do is we're going to take a Havoc body, and when it is damaged or destroyed, it's going to be split into multiple child objects. And then lastly, impulse is the intensity of a collision, which is calculated based on the mass and relative speed of the two objects colliding. So we use a single event per physics behavior with nested switches to select the appropriate content. And each material has multiple masses, and each mass has multiple impulses. So within those nested subsets, we assign the various layers that are going to make up the composite sound. I'll go into a little more detail on each of these switches here in the next couple of slides. The first one is material. We have 5 materials in our game: concrete, carbon dark, metal, steel, and glass. Concrete is going to be the cladding on the sides of buildings. The carbon dark is going to be the roofs and the floors of the buildings. And the metal is going to be kind of a random mishmash of different metal support structures and panels and things like that. Steel is different from metal in the respect that this is the steel beams that make up the building. So a building is a metal skeleton with concrete cladding and carbon dark cladding attached to it. And then glass is the glass windows and panels. And a little note about the glass is that they are all the behaviors are handled by GPU only. So once they break, it's all just GPU objects. All right. The next switch is mass. Each material type has a unique set of mass thresholds that determine which mass category a particular Havoc body or GPU object falls into. We also then track the mass of the object as a percentage of the range of the values within its mass category. And this value drives an RTPC called phi impact mass percent, which is used to scale pitch and voice volume and makeup gain. And that helps us give an additional gradient from the smallest to largest object rather than just having a 5-increment stepped system. And then the third switch is impulse. Now, for each mass set, for each material, we have a unique set of impulse thresholds. And those are going to sort the collisions into impulse categories. Any collision below the minimum threshold is just going to immediately disregarded. The rest of the impacts then get sorted into low, medium, and high intensity impacts. And like the mass thresholds, we track the impulse values relative to their ranges and drive an RTPC called phi impact impulse percent. And this scales volume and makeup gain to give us a smoother gradient over our intensities. All right, we're going to focus heavily on the impact system in this talk, but there's several other behaviors that are worth noting, so I'll give you a quick rundown of each of those. Damage ballistic, this is the sound of projectiles impacting Havoc bodies or static geometry, specifically projectiles, not rockets and grenades and things like that. In both cases, the impacts are going to generate GPU chunks at the point of impact, and this supports the idea that you're chipping away little pieces of the world as you shoot it. A Havoc body sustaining enough damage will eventually be destroyed. And like I said before, it's not just going to be simply removed. It's actually going to split into multiple child objects. In terms of content for that, we have unique content sets for each size of each material. Turbulence system is very similar to the props turbulence system that we discussed earlier. It's worth noting that turbulence only plays on Havoc bodies and not GPU chunks. Again, we created content sets for each size of each material. Just like props, we use multiple layers with unique attenuations. So we have turbulence loops, turbulence resonance, and turbulence sweeteners, and LFE. Scrape is very similar to turbulence, but obviously it requires the object to be in contact with another object or static geometry in order to play that sound. The main difference between those two is actually, rather than a sound seed patch for our turbulence, our scrape loop is a blend container with 3 different speeds of scrape loops. And that's driven by the relative scrape speed, RTPC. OK, impacts. So a physics chunk colliding with another physics chunk or static geometry. This uses the 2 hands clapping method, except when a physics object is striking static geometry. We do not play a sound on the static geometry object. We have multiple layers for each material and size set. So again, impact, resonance, sweetener, and LFEs. Each material and size set has separate content for each impulse, low, medium, and high. We also have some additional size sets that were added toward the end of production. Tiny for concrete and carbon dark and glass. And we also created a new one called enormous at the very end, because we found that we had very, very large pieces that just kind of need a little extra cinematic oomph. And then lastly, carbon dark and concrete are further subdivided into single and merged impact sets. And we'll talk a little more about that when we get to collision merging. So enough talk, here's some videos. This is destruction audio only. We like explosions. And so here's everything all together. So this is going to be all the weapon sounds as well as some building destruction on top of that. Just one rocket, that's all it takes. Great, so some of you might have seen some of our objects kind of magically disappearing in those last videos. This is a system called DRes, and it's a system that was developed to clean up and remove objects from the game. This helps performance by removing objects that no longer need to be tracked by the game, but it also ties into the narrative of multiplayer, which is that you are inside a combat simulator. And so we created some content to support that narrative. And we settled on making size-based variations, but not material-based variations. So I'll play you those now. All right. So as we started getting the physics simulation into pretty decent shape, it became apparent that we weren't going to be able to rely on that alone to make a compelling audio experience. We needed to create the sense that buildings aren't just a collection of materials that fall down, and we needed to add some kind of special sauce to make it give a little more cinematic vibe. And so this is where building destruction comes in. Thanks. So before we get started on that, a few terms to understand. Buildings are a prefab collection of destruction materials that are attached to a superstructure of steel beams. What the player perceives as a single building is actually often multiple buildings, and that's for performance reasons. So if you see a big skyscraper, it's probably 3 or 4 buildings kind of stacked together, or buildings. Superstructure is the steel skeleton of the building, and attachments are the walkways and ramps that connect buildings to other buildings or static geometry. All right, so buildings enter destruction states depending on the amount of damage they've sustained. Each of these states has a unique treatment that enhances the destruction experience and also gives the player some feedback about the state of the building. Health of the building is equal to the percentage of attached material. So it's basically how much concrete and carbon dark is still hanging on to the infrastructure. I'm going to walk you through each of these states here in a second, along with the audio treatment. The first one is a damage state. So once we pass a certain threshold, we go into a damage state, and we cover that with soft metal creaks and groans on a randomized delay. Now, for emitters, we use the superstructure joints of all the steel beams coming together. There's a lot of steel beams on a lot of joints, so there's probably too many to track as emitters. What we actually did is merge those within a 5-meter radius, and that kind of narrowed down the number of emitters to a kind of a reasonable number. And then finally, we use attenuations and azimuth to really help with the directionality of the mix. So if a building is moaning and groaning, it should be very apparent which one is doing that. Critical is basically an extension of damage. We're going to make the creaks and groans. We're going to use more severe content, and we're going to use it more frequently. We also use the same exact emitters as the damage version does, the superstructure joint emitters. All right, so now this is pre-collapse. I have to kind of take a step back and explain a few things here. So once the health of a building has reached its collapse threshold, it will collapse. But if multiple buildings are in this state, we can't have them all collapsing at the same time for performance reasons. So this is where the collapse queue comes in. If a building is already collapsing, any additional buildings that cross the collapse threshold are going to be added to the collapse queue, and they're going to wait their turn to fall down. So when a building is in the collapse queue, we refer to the state as pre-collapse. When a building enters the pre-collapse state, we trigger a one-shot event from the center point of the building that signals that the building is ready to collapse. It's not going to fall down yet, but you know it's coming soon. We also trigger a looping set of metal groans and an LFE rumble loop at the base of the building, and those have a narrow attenuation. So the first sound, the one shot, is basically to tell everyone in the nearby map that this building is going to come down, and the loops at the base are really to kind of sell the point if you happen to be in the immediate vicinity of the building. So building collapse, it's our turn. We get to collapse now. We're going to, all the superstructure joints are going to break, and the building is going to crumble down. Similar to pre-collapse, we're going to trigger an event signaling the start of the state change. In this case, we use content that's a bit more punchy and designy, and we also add an LFE sweetener to that one shot. And then we also have a looping rumble sound, an LFE event that's at the base of the building. Again, narrow attenuation, so only for those players in the immediate vicinity. And lastly, you'll hear attachments. So these are the walkways and ramps that are attached to the building falling down. Those constraints are going to break, and that's kind of like a metal whiny snap kind of sound. All right, so what does that all sound like? In this video, I'm going to show you just the building destruction. We are in a critical state, right? So we're not ready to collapse yet, but we're going to be exhibiting all of those critical state moans and groans. And then it's going to cross over into the collapse state, so you'll hear the one shot and a descending kind of design sound that helps sell the idea that everything's coming down. So this is just building destruction, none of the procedural destruction audio here. That kind of metal snap you heard on the inside was one of the external constraints from a walkway that was breaking. All right, and now here is all audio up, another building coming down. All right, so how do we manage that level of chaos and have it play sounds that even feel remotely appropriate? The challenge we have is that during a 10-player match, if everyone's just letting loose on everything in sight, you can have over 10,000 collisions per frame. Right? So we can't send all of that across the network. So we have to optimize those messages to limit both the network traffic and then also just not swamp Wwise with a million events. And so here's how we do that. So we start filtering on the server. Our goal here is going to be to reduce the number of collision messages that we're sending from the server to the client. Each of these red boxes is an opportunity to discard some of these collisions. And this is a little hard to read, so I'm going to give you another version of this graph that's a little bit simpler. We'll just kind of focus on one branch. You can assume that any of these dark gray boxes are going to branch identically as the one on top here. All right, so we start on the left with all of our Havoc body collisions. And then we're going to first sort by material, and then by mass, and then by impulse, which leaves us with buckets of collisions that are based on those three parameters. At the impulse filtering stage, we can discard any of the collisions that are below our minimum impulse threshold. Right? That's our first opportunity to get rid of some messages. The remaining material, mass, impulse subsets are each going to have a corresponding attenuation in Wwise. For each subset, we can check the distance of each collision against the attenuation values from Wwise and discard all the collisions that fall outside those attenuations. So in other words, these are collisions that Wwise would throw away anyways, so there's no point in sending them from the server to the client. So now we have a filtered list of all the collisions that we've deemed relevant to the client, but we still have too many, so we have to trim them down a little further. And so we're going to send them to the collision merging system. This is our merging system for collisions. We sort the filtered collisions into different buckets based on their distance from the listener. And then each of these buckets has its own set of merging parameters, sample period and combine radius. So when a collision occurs in one of these buckets, it will look for other similar collisions that occur inside the combine radius and within the same sample period. We then merge these eligible collisions into a single merged collision message. Now, each merged collision registers how many bodies were merged together, and that data is going to be sent to the client as a new collision message. So as you can see on the right side of our settings here, if you look at those closely, you'll notice that closer collisions are merged less aggressively. And this allows us to have more accurate timing and panning for collisions that are close to the player. At greater distances, timing and precision and precise panning are going to be less crucial, so we can sacrifice a bit of that accuracy for the sake of performance. All right, so now on to the client. OK, here we have the filtered and merged collisions from the server being combined with the GPU chunk collisions, which are generated by the client. Okay. The GPU chunk collisions are first filtered by a screen culling effect, which basically disregards collisions that are off screen. And then we apply the same style of filtering and merging that we did for the Havoc bodies to the GPU collisions. Once that's done, we can combine them all together, the Havoc body collisions and the GPU collisions. And we're going to send them to our importance filter, as you see on the top right of our diagram here. So this is now a list of all of the collisions ranked in order of importance, where importance is determined by the distance, the mass, and the impulse values of each of the collisions. We have a max collision setting, which is going to determine how many play events we can send to Wwise at the same time. And then we have a hold time and a release time that are a little bit hard to explain at this point, but I'll show you a little more detail on the next slide. Will make a little more sense. So here is a simplified version of our importance list. So I've listed our hypothetical importance values on a scale of 0 to 100 to make it a little easier. In reality, our importance values are astronomically high. And you can assume that collisions with a higher value have some combination of being closer, bigger, or faster than the collisions with lower values. Okay. So here's our hypothetical situation. On the first frame, we have 10 collisions. Our max collisions is set to 6, so that means only the 6 most important are going to be passed to Wwise to trigger play events. The remaining collisions are just simply going to be disregarded as if they never happened. Now, in the next frame, a new collision occurs with a higher importance than collision E and F. Okay, so collision E is going to be demoted to slot 6, but it will continue to play because it's still within the max collisions value. And collision F is going to be demoted to slot 7, which is outside of that value, and so it's going to be faded out over 2 frames. And that just kind of keeps us from having nasty pops and clicks when we shut down our impacts. So, take a drink. So this works pretty well most of the time. But occasionally the tail of a high importance impact will be playing out and hogging one of these importance slots, right? So another impact that has a slightly lower importance can be bumped off the list or just not even let onto the list because of this tail. Our impacts and our bodies are more important than our tails, so we want to kind of have a system that allows for that to work. So let's say our importance list is full, and we're currently playing the top 6. And a second later, as these sounds are all playing through their tails, another collision happens, and it's added to the list with an importance value of 1 less than the collision currently in slot 6. Now, since the importance isn't high enough to move it into the top 6, this collision is just going to be disregarded, and arguably it's an important sound that we really want to hear. So to remedy this, we added a hold time and a release time to the importance filter, which allows the impact to remain on the importance list for the duration of the hold time, and then it fades the importance value down to 0 over the release time. So this allows more important transient sounds to kind of take over from tails. These are our optimizations. So max collisions we had set to 6. Collision impact fade time, that's when it gets bumped off the list, is 0.067, which is 2 frames. Our importance weighting, so this allowed us to decide what was the most important factor when determining the importance value. And you can see here that mass, we overwhelmingly decided that mass was the most important thing. And then we have our importance hold times and release times that I just described there, 0.6 seconds for hold time and 1.1 seconds for fade. All right, so now on to Wwise. Okay, the last stage is Wwise itself. The PlayFi impact event triggers are going to trigger appropriate content based on their switches, material, mass, and impulse. You can see here that the impact layer also has another switch called body count, which is the number of merged bodies that are embedded in a merged collision. So we use this to select single, few, or many impact layers. The resonance, the sweetener, and the LFE play the same content regardless of how many bodies in there, so we just really used it on the impact or the kind of the transient sound. Each layer has its own attenuation and HDR voice volumes, and so these settings can potentially push the voice volume of a sound down below the voice volume threshold, which would immediately kill the voice. And this opens up a slot on the importance list. So whenever for whatever reason, if an event stops playing its sound, it opens up a slot on the list. Any voices that are not killed at this point are going to continue on to the playback limits that are set in the master audio bus and the project settings. So if you make it this far, you're almost there. If either of those are exceeded, sounds with the lowest voice priority are going to be killed. Okay, so if you make it all the way to here, we will actually hear a sound. So we start with 10,000, get down to possibly 6. All right, this is our priorities diagram here for destruction. We gave destruction physics a pretty wide span of our priority map. So this is from 20 to 65. Things that are above 65 are going to be essential gameplay. These are going to be music, announcer, weapons, skills, explosions, important barks, that kind of thing. And then below 20 is going to be secondary movement, some map ambience, the derez behavior, things that are just not super essential. And a last note on this is that all of our priorities in our game decrease to 0 over their attenuation. All right, so just a quick glance back at our original challenge here. So we started with 10,000 plus Havoc collisions. On the server side, we filtered the Havoc body collisions, and then we merged them. On the client side, we generated all our GPU collisions, filtered them, and merged them, and sent all of those with the Havoc collision, the Havoc messages to the client-side importance filter. At that point, we decide which are our top contenders, and we send them on to Wwise, in which case Wwise handles all the voice management, and we hear hopefully something that sounds reasonably appropriate for what we're seeing. I want to take a few minutes to talk about turbulence in multiplayer for destruction. So turbulence in multiplayer destruction works in the same principles as prop physics, the prop physics version, but we had to limit it really severely for perf reasons. Turbulence has a max per frame value of 3, meaning that only 3 objects can play turbulence at any given time. And this limit is set up on the server side because of network traffic, right? If we send all of our turbulence messages to Wwise and let that limit sorted out, we've already swamped our network traffic. So we also ignore any body outside of 60 meters. Our centimeters is our our unit in this game. So outside of 60 meters, we just ignore turbulence. And then also, if an object is traveling less than 3 meters per second or greater than 50 meters per second, we also ignore it. The turbulence importance value is calculated based on mass and speed. And again, we have an importance system for turbulence. It works on the basic same principle as the impact one. And if you get bumped off, then you have a turbulence fade time of 2 frames. So I'm going to play some videos to show you the turbulence system just soloed here. Or not soloed, but. All right, so you can hear it's pretty aggressive, right? It gets out of the way really quickly. When you combine it in the full mix, though, more often than not, it actually works out pretty nicely. So I'll give you the full mixed version of Turbulence. Cool. I'll play a couple last vids to wrap up, just some kind of full destruction mayhem. One more for giggles. All right, so as you can hear, it's not perfect, but we were pretty proud of how far we got with what we had. So with that, I'm going to say thank you for listening.